Hello everyone. A very good day. I hope everyone is doing well. So today we will try to solve a problem of rearranging linked list. It's a very interesting problem as it covers many of the concepts of the linked list. And this problem I received from this website dailycodingproblem.com. So you can subscribe to their mailing list and daily you will get a coding problem to solve from them. So it's a free subscription. And the question is like this. Say, given a linked list of numbers and a pivot k, we have to partition the linked list so that all the nodes less than k come before nodes greater than or equal to k. So for example, 51803 is the linked list, and suppose pivot is k equal to 3, then what will happen is all the nodes which are less than 3 need to be at the beginning, and all the nodes greater than equal to 3 will come after them. So here the nodes less than 3 are 1 and 0, so they will come at beginning. It need not be in any order, ascending or it can be in any order. And then after this elements less than the pivot have appeared, then only the other elements would appear. Okay, so it's pretty. Let's see some more examples. Say this is one. Let's say let's create one more example as 6, 8, 2, 1, 30, and say 10. And let's say our pivot is 8. Okay, so all the elements which are less than 8 will be at the beginning, then the elements which are greater than 8. So the answer should be, the 6 should be at the beginning, the 2 should be at the beginning, the 1 should be at the beginning, then we can have 8, 30, and 10. Okay, so I hope you got the idea. Whatever the pivot is given, all the elements less than the pivot need to be at the beginning, and all the elements equal to or greater than pivot needs to come after the smaller elements have appeared. Okay. So this is a pretty pretty natural. I mean, pretty naturally we can solve it. So let's take this problem itself. What is given in the question? So the given problem is say 5, 1, 8, 0, and 3. So what we can do is traverse through every element and we will see if the value is less than the pivot. In this case, say k is 3. If the value is less than the pivot, for example, this one will not do anything. We'll let this be. But if the value is greater than equal to pivot, then what we can do will simply take this element, remove from here, and put it at the end. Okay, and in this way, suppose we come here, we see the value is greater than the pivot, we remove from here and put it at the end. So in this way, when we do it, at the end, what we will find is basically that all the elements which are less than the pivot, which were untouched, they will remain at the beginning, and all the elements greater than equal to pivot, they will come at the end. And in this way, we can solve this problem. So to write this pseudocode, it's pretty straightforward again. So we will simply repeat uh, for for all elements. Okay, we'll repeat, and what we'll do is check whether if say current node dot value, if current node dot value is less than k, the pivot, we will simply move to the next node. Okay, and if it is not, okay, if this is the case, or else we will eliminate this node, eliminate the current node. Forgive me for my handwriting. So eliminate the current node and then attach it at the end. Okay, attach at end. So pretty much this is the pseudocode. For every element, simply compare it. If it is less than k, we'll do nothing. If it's greater than equal to k, we will attach at the end. Okay, so the logic is pretty clear now. But let's see how we can do it in the terms of linked list. Okay, so in the terms of linked list, we have to do some operations. So let's see. So let me come here and let me bring. So this is example of sorry, a linked list, how it looks like. Oops, I need to just bring this on the right for you. Can I? Okay, fine, no problem. Yeah. So basically, the linked list, looks like this. So we'll have the every node will have a value and a pointer pointing to the next address, and then we have these two special nodes called the head and the tail nodes. Okay. So let me bring this here, and okay, this is the tail node. Say the tail node, and so as I said, we have to do majorly five operation. So because we'll be traversing over all the element of the linked list, we need to know the length of the linked list so that we can stop after we have seen the last node. Because if you remember, our algorithm says that we'll be attaching the deleted node at the end, so it will keep on moving if we just don't keep track of the number of nodes in the list. So first of all, we have to estimate the length of the linked list. Then we need to also identify the tail node if it's not given in the problem, because we'll be attaching the deleted node at the beginning, or while we're traversing to the end. So we should know where it is, so that we can simply point out the next of the tail node to the deleted node. Then we have to traverse the linked list. That's we'll do anyway. And then we have to delete the node. Now deletion could be either at the beginning, either we could remove this 5, or we have to remove somewhere, like this one is at the beginning removal, or this one is at the middle removal. So there is two places we have to see how we can remove the node. And then there is attaching of the node to the end. So let's see how we can do this. Yep. So let's see how we can first traverse the linked list. So basically, traversing is simple. You just keep track as this is your current node, okay, C node, and then you simply, in order to traverse to next element, you make the current node is equal to current node dot next. Okay, and you keep on doing till you find that the next node is equal to none. So in this way you can traverse, simply current node is equal to current dot next. Okay, so this is the traversing. Then to identify the tail node, so when the current dot next is equal to none, then tail becomes your current node. Tail node is equal to the current node. So in this way we can identify the tail node. Okay, now these two operations are important, the attaching at the end and deleting either at the middle or at the beginning. So suppose if you want to, let's take the fifth one, attach new node at the end. So suppose there is a new node which got deleted from here. Say this is the 5, okay? And this is pointing to some address, and this is your tail node. So it's very simple. You just make tail dot next. Okay, tail dot next to point to here. Okay, I mean this is suppose the tail, you simply make it point here, and then this node next you make it point to none, and you make this one as tail. Okay, so in this way we can attach the at the end. Simply make the current next of the current tail as the new node which you want to attach, and that new node which you attach, you make this as tail and make the next of this node as none. So this way you can attach to the end. Now let's come to deleting. So if we have to, delete at the beginning head node, it's not a problem, because yeah, we can simply, uh, this is suppose the current node, okay, and you want to delete it. You can simply put this, uh, we point the next of this tail to this, and we make the next of this equal to none, so it gets deleted from here, like there is no connection in the linked list, and it gets it gets away, and we can make this as our head. That's the the first node of the linked list. So simply put the next of this as none, there is the connection breaks, and then this one you put as the head. However, suppose if you have to delete in the middle, say this one, then in order to delete it, obviously we can make the next of this equal to none, so it breaks the linked list, but we have to make a connectivity from the previous node. So we have to keep track of the previous node as well, and the next of its previous node will then point to the next of the, suppose this is the current node, okay, and this is the next node, and this is your previous node. So what you can do is the next of the previous node will point to the next of the current node, and the next of the current node will simply become none. So in this way we break this one from here. Okay, so now I hope this makes sense. So we can basically have, some pointers. Let me just re-erase it, uh, and then it will make sense. So whatever we discussed, what are the operations that will be involved and what is the pseudocode? Let's put all together into an algorithm and let's try to run through this code and see that it makes sense. Okay. So I have printed out the code here for reference, but let's walk through it. So let's assume we already know the head node is given and we somehow also calculated the length of the linked list, which is equal to 5, and we know the tail node. Okay. So what we can do, let's first start with the first operation. So w let's write, say this is my 5 pointing to 1, pointing to 8, pointing to 0, pointing it to 3. Okay. So this is my, say, step 1. Okay. Now before starting, what we'll do, so we already, as we said, we have a head node. Let me call this as H. Okay, and this as T, the tail node, and then whatever our head node is, the first node or the current node will be this. So let me call this as my current node. Okay, so this is my current node, and since we don't have any previous node, let me have a previous node pointer as of now as none, simply none. Okay, this is my previous node. This is the head node, the first node given to us, and we'll consider the current node is equal to the head node. Now we'll start the loop. This is the first step. Now, if you remember, there were two conditions to check. One is our current node value less than k? If it's less than k, we don't do anything. I mean, we don't delete, we simply traverse to the next. But if value is greater than k, then we have to delete it. And deletion can happen at two places. Either we have to delete the head node itself or some middle node. Okay. So this code has given this two condition, but let's walk logically first. So this is our current node. What we'll do, we'll simply check if current node dot value is less than k. Okay, so in our case, 5 less than k. No, this is not the case. So obviously, then we have to delete the node because it's greater than k. Now, in deletion, as we said, we have two conditions, head or middle. So how will we know whether it's a head node or not? So we can know by two ways. One is if the previous node is none, then it's a head node. Or if the current node is equal to the head node, then also it's a head node. That's pretty natural to think about. So either of the condition you can use. So in our case, this is a head node. Okay, so how we can delete a head node? So first of all, before deleting any node, we need to identify the next node, because if we delete, that's gone. So we'll lose that link with the entire linked list. So our first of all, we'll identify the next node, and next node will simply be the current node dot next. Okay, so the sorry, here the next node is equal to the current node dot next. Now once we have it, we have to delete this. Now deleting in linked list is pretty simple. We have to just break the link. Okay, this was pointing to this. Now what I'll do, I'll simply make it point to, say, none. Okay, now this, you can imagine this as, this is none, means it's like kind of, outside. Outside means it's not connected to the linked list. So assume, let me just put it a bit uh, down here. So let's take, okay, this is, say, the current node, and so, oops, it was a rubber. Yep, head node is still this, but I mean, just assume, yeah, this connection is still there. I mean, and the previous node is still none. Now what we'll do, this is kind of deleted from here. Now we have to attach it to the end. Now attaching to end is very simple. So in the tail node is the one, tail node basically points to none. So what we'll do, we'll take this none next pointer of the tail node. Okay, so you can see tail node dot next equal to current node, and we'll simply make it point to this node. Okay, and since this becomes our last node, then this will become our tail node. So this will no longer be our tail node. This is, sorry, 3. This will be our tail node. Okay, so this guy becomes our new tail node. So that's what I'm doing. I am doing tail node dot next equal to the current node, tail node equal to current node, and now this will no longer be current node. This will become our current node. Okay, so simply it will be, this will be our current node, and this is no longer our current node. And now the head, which was, this, now head will be pointing to the current node because this has gone to the end, and this is our first node. So we'll simply do head equal to current node. Okay, so now this pointer will, now this will become head, and then there is no link here, and so simply this is our tail. So simply to make it much cleaner, now we can simply shift it here. So let's say this was 3, now this becomes our 5. 5 is pointing to none. Okay, and this is our tail node, and I will just erase this for now for much cleaner understanding. So this was our step 1. Now the next we'll move step 2. Okay, step 2. Now this is our current node. This is the head node. So let me just write it here. It will be, say, 1, 8, 0, 3, and 5. 5 pointing to none. This is our tail, and this is our head now. And the previous node is still pointing to, some none entity. Okay, and this is our current node. Perfect. Now we'll check if current node value is less than k. So 1 is less than k. Yes, it is right. So we don't have to delete it. We have to just traverse ahead. So, when we traverse ahead, simply we can make this as our current node. But before that, we have to make this as our previous node. So our previous node will now simply, instead of none, it will be this node. So now our previous node is equal to the current node, which is this node, and our current node become current node dot next, which is this. So this becomes our current node, so basically this one. Okay, and that's it. This is step 2. Now let's come to step 3. Now in step 3, this is our current node, so I'll just kind of repeat this step just so that we are in same page here. Copy it, and let me see if I can paste it, how I can do that. Yeah, so let's me, okay, I think writing would have been much faster, but yeah, okay, no problem. So let's assume this is our step 3 condition. And yeah, now we'll check, is 8 less than k. So 8 less than k, which is equal to 3. No, so we have to delete it. And now if you see, this is in the middle. Okay, so we have to, do some more step. So what is the idea? First of all, we'll identify the next node. So the next node is basically current node dot next. So this becomes our next node, and then we will make the current dot next point to none. So simply we will, instead of pointing it here, it's pointing it to none. It means we are deleting it. Okay, it's pointing here to none. Now now we want to make this as our last node. So let me just bring this here. Let me maybe rub it and just assume that this becomes independent. So it will be basically some 8, which is pointing to none, and which was our current node. And the link is still there, okay, for now. This link is not broken yet, okay. Now what we do, this was the tail of next, which was supposed to be none. We will not let it be none anymore. We will simply make the tail dot next equal to the current node. Okay. So this become our last node, and now we will rename this as tail. So this will no longer be tail. Now this guy will become our tail. Okay, perfect. And now this is no longer the current node. The next node will become our current node. So this is our current node. So we have done everything. This has become the tail, but now we have to break this link and create the link of this with this. So what we'll do simply, this is our previous node, which we have identified. So we will simply break this link by doing previous node dot next equal to current node. Okay. So this link will break, and I'll create a new link from here to here. So this is what it looks like. And if I make it a bit cleaner, then yeah, this will be like this. So 5 would be then pointing, oops, 5 would be pointing to 8, 8 is pointing to none, and this is my tail, and this is my previous node, and this becomes my current node. So let's go to the next step, step 4. Okay, so let me go to step 4. So you can see, already the 1 and 0 are already in the right place, but I mean, yeah, 0 we don't know yet, but at least 8, 5 they're on the right side, and 1 is already in the right place. Now in step 4, what we'll do again, we will check whether current node is, so current node is 0. 0 is less than 3. It's right. So if I rewrite this, so let me take 1, 0, 3, 5, 8, none. This is my previous node, which also is my head node, and this is my current node, and this is my tail node. Okay, let me create some space. Yeah. Now we check that 0 is less than 3, right? So we don't need to delete it. We have to just then follow this, that the previous node will become the current node. So this will become our previous node. Okay, and we will get rid of this, and then current node is simply current node dot next, which is 3. So I will simply create this as my current node. Okay, so that's it. In this step we don't do anything. Now we come to step 5. Okay, this is our final step, and how we'll know it, because of the length of the list. So because this list can keep on appending at the end, it's not like we'll just keep on looping. So we have to break after we have seen each element in this. So 3 is the last element, based on the length. So now, for example, in this case, this looks pretty much same like this. You know what? It's faster that I just write it by myself. So I have basically 1, 0, 3, 5, 8, none, and this is my head. Oops. Uh, I'll use the same color, the orange one. This is my head. This is my previous node, which is 0. This is my current node, and this is the tail node. Okay, I'll create some more space. Yeah. Now what we'll do, we'll compare 3 is less than k or not. So we'll see 3 is less than k. No, 3 is equal to k or greater than k. Then we have to delete this element as well. So how we can delete it? So it's pretty simple now. We will first create the next node, which will be current node dot next. So this will become our next node, and then in order to break this link, we'll simply make the point, we'll break it, and this is 5. We'll make it point to none. Okay, and so what I can assume, as we did earlier, let's keep it a bit, let's bring this 3 outside. So we'll have this 3 somewhere here pointing to none, and this is also supposed to be our current node. And right now the link is not broken. Okay, there is still a link. So what we'll do, because we need to attach it to the end, the whatever tail node was there, that there next will not put as n, will simply put the next as this current node. Oops, what I did. Oh, it was 8. So their next will now become the current node. And because this is now supposed to be last node, we will simply make this as the tail node. Okay. So we'll make the tail node as our current node. And now we need to, because we need to delete it, we have to break this link. So what we can do, the previous node dot next will be, okay, first of all, we'll create this as current. Okay, this will become our current node. And this will no longer be our current node. This is, a tail node. And now what will we do? We simply create the link here. We break it. And how we'll do it? Simply a previous node dot next equal to current node. So previous node dot next will simply point here, and this link will break. Okay. So now at the end, it will look something like this. If I make it much cleaner, it will be like 1. Oops, it will be 1, and then 0, and then 5, and 8, and 3, and none. So this is our tail node. This is supposed to be current node, but we have already visited 5. This is our head node, and this is still our previous node. But sorry, previous. Let me. Okay, I'm still new to this. So this is our head node, and this is our previous node. Now, because we have looped over every element, we'll simply break and give the link of the head. We'll simply return the link of the head. And now if you see, our link list is 10583. Okay. So we started with 51803, simply it was 51803, and this was our pivot. So all the elements which are less than the pivot should come at the beginning, so 1 and 0, and then all the elements are coming at the end. So this is the algorithm. And if you look at the space and time complexity of this, so if we just see, so basically we are looping only once over it. Yeah, we'll loop one more at the beginning to find the length, so which I did not show it here. I'll show it in the code. But basically, to find out, we'll have this say O of n. So if we are assuming the time complexity, O of n, to count the length and identify the tail node, plus in order to do all these operations that we did, we'll be looping one more time to the element. So O of n, which is equal to O of 2n, which is approximately, which can be approximated as O of n time complexity. And space complexity, I don't think we are taking any, extra space. Whatever we are, I mean, taking space, we are deleting that space. So it's like, I don't think there is an extra space. If I understood correctly, I don't think we created any extra data structure to store anything. So it will be simply O of 1. Okay. So this is the logic, and I took some time to explain it because it gets confusing with so many connections. And if you understand it, then I think you can do any of the list program, list problem on list, list based questions.